Hi, good evening. Am I audible?
Yes, ma'am.
Okay. Yeah, sure, we'll discuss that. One second, let me just share my screen. Yeah, what kind of questions do you have? Anything in particular? Or
Ma'am,
yeah.
yes, ma'am. Particular questions from those assignments.
Hmm. Can you maybe share, like, read what is the question?
Yes, ma'am. One second.
Hmm.
Ma'am, one of the question was, what
Hmm.
will be the correct statement regarding the substitution of coordinated ligands in NiNO4 and
Hmm.
CONO CO3 CO whole thrice, where the CONO bond is nearly linear? There were four options. Both follows associative pathways, both follows dissociative pathways, associative and dissociative respectively, or dissociative and associative respectively.
Yeah, so this one is related to first the number of electrons. So whenever the number of electrons in a complex is say 18 electrons, then it cannot go through associative pathway, because associative pathway is like when a ligand comes and attaches to the metal first, to the complex, then another ligand will leave. Dissociative pathway is like first one ligand will leave, then the incoming ligand will come and attach. So in that case, you'll first have to look at the number of electrons. So most of the time, when the number of electrons in the complex is 18, then and if it is a organometallic compound, then it does not like incoming ligand, because it will make it to 20 or more. So I will explain in this class why this 18 electron rule is followed for this organometallic complexes. So you have to look at, if it is 18 electron, then definitely it won't go to associative pathway. It should be going through dissociative pathway. But then if the complex is like 16 electron or some 16 electron, I mean lesser than 18, it can be 16 sometimes. In that case, it can be associative. And sometimes we can see that it is neither associative or dissociative. It is like intermediate associated dissociative kind of thing. So first you'll have to calculate the number of electrons. I don't think I have that question in this slide now, I mean this session, but at the end I can get that question and we will discuss that.
Okay, ma'am.
Yeah.
Ma'am, one more I did
Hmm.
have that. That is also related to 18 electron one only.
Okay.
The
uh,
question is 18 electron rule is valid for octahedral complexes having pi acceptor ligands or sigma donor ligands or pi donor ligands or all of the above.
it is for pi acceptor ligand. So that also, as I said, I have separate slides for why this 8 electron rule is followed, and there I think it will be clearer for you. If not, we will discuss again during that question.
Okay, ma'am. Okay.
Can we say wait for 3 more minutes until 7:05? Then we will start. Okay, maybe we can start now. Um, my screen is visible to everyone, right? And I am audible, right? Can anyone respond? Is my screen visible and am I audible?
Yes, ma'am.
Okay, so we will be. My name is Anach Mariachedi. I'm a PhD student in the Department of Chemistry, IIT Tirupati, and this is my email ID that you can contact at any time if you have any doubts. So, as you know, we are dealing with the problem solving sessions in this Basics in Organic Chemistry course, Inorganic Chemistry course. So, so in this session, we'll be solving some of the questions related to the week one and week two lectures. So whenever you have a doubt, you can stop me in between, and we'll. This is like an interactive session, so we will solve the questions together. So when I ask you to answer the questions, you can either put it in the chat box, or if you're comfortable enough, you can like directly speak to me. Okay, so let's start. So this question is pretty straightforward. Which of the following configurations would you expect to have the highest ionization energy? So first, highest second ionization energy. This is the keyword here. So first, we have to know what is ionization energy. So ionization energy is essentially the energy required to remove one electron from the neutral atom, like the first ionization energy. If the second ionization energy, it means that after removing one electron, you have one configuration, and from that again one electron is removed. So that will be the second ionization energy. Okay, so first these all are like neutral configurations. So and they are asked us to like they have asked us to take the second ionization energy. So in order to find out which one has the highest energy, first we have to remove one electron, then we will look at the corresponding configuration, then remove the second electron. So first is 1s2, 2s2. So if you remove one electron, it will be 1s2, 2s1, right? And if we remove one more electron, it will be 1s2, 2s0. Then the next one will be 1s2, 2s2, 2p4. If you remove one electron, it will be 1s2, 2s2, 2p3. Now again, if we remove one electron, I don't like 1 second. 1s2, 2s2, 2p2, right? So so on. So I am not going to write all, but you get the idea, right? So for the third one, if you remove one electron, it will be 1s2, 2s2, 2p6, and 3s1 is removed. Then the next one will be 1s2, 2s2, 2p1, 2p0, right? This is 3s0, this is 2p0. Now we have to look at these configurations, like this 1s2, 2s1, 1s2, 2s2, 2p3, then 1s2, 2s2, 2p6, 1s2, 2s2, 2p, 1s2, 2s2, these configurations. Now we have to look at where it will be very difficult to remove the electron. So do any of you have any idea which will be the answer?
Ma'am, it's option third
Yeah, option third. Why?
because it acquires noble gas configuration.
Right. So exactly this is the answer, the option three, because if you remove this electron, it is essentially the noble gas configuration. This is a closed shell. So this has an extra stability. And if you think about this one, this is also a closed orbital, but not a shell. This also has a better stability, but this one has the highest stability. In this case, it just becomes three. It is a half filled state, but it is also stable, but compared to this one, it is less stable. And this one is just, it will become 1 2s1, so it is also half filled kind of stage. But still, if you compare all these, this additional stability, higher stability is for this completely filled this shell. If the stability is more, it means that the energy required to remove that electron will be so high. So in that case, because of that, this third option will have the second highest second ionization energy. So do you guys have any doubts in this question?
No, ma'am.
Okay, so I'll move on to the next. Okay. Okay, so here the question is, which is the correct order of electron affinity of halogens? So electron affinity or EA is the energy required to add an electron to a system. So like whenever the energy, or we can say that it is the energy released when an electron is added to a system. This is a neutral atom or something, then we add an electron, and because of that, is the energy released or do we have to give energy? That energy requirement is the electron affinity. So these all are the halogen groups, halogen elements. So if I write it in the, in the group order, first will be F, then will be chlorine, then will be bromine, then iodine, then astatine. So in this case, one second. Yeah. So in this case, what happens is, down the group, the size is increasing or decreasing. The size down the group will increase or decrease. You can put it in chat box
Increase.
also. Yeah,
Increase.
yeah, size will increase down the group. So, and we know that all these are highly electronegative in nature, and these halogens are the 17th group, right? So from the first group to the 17th group, around, along a period, the size decreases, right? From, if you go
Yes,
from,
ma'am.
yeah, so right to left, I mean left to right, the size decreases, which means that F is like, in its own period, it's a small element. Same goes for chlorine. But when you look at the same group, then F is the smallest and astatine is the largest. So now the thing is like, whenever the atom is small, it means that the nucleus has more control or more attraction over the last electron, or we can say that the that is why the atom is small, because the nucleus is attracting the last electron so much so that the atom is contracted, and that's why we have, along the period, we see that the size decreases. So in this case, if we add, we naturally expect that since fluorine is more electronegative than chlorine, it is also small. Because of that, this fluorine might be having the highest electron affinity. But here it is not the case, because fluorine, as you know, has like 2s and 2p, that is the second shell. Then chlorine will have 3s, 3p, 3d, and so on. Then bromine will have 4s, 4p, 4d, 4f, so on. So if you add an electron, this is coming to this p orbital here. So for fluorine, the case is that the fluorine is so small, and already we have like 5 electrons in this 2p orbital. Because of this, there is like so much electron repulsion, because already the fluorine is small and there are 5 electrons in the 2p, and because of that, inside the 2p there will be so much electron repulsion. So if we add one more electron, fluorine does not really like that because of this electron repulsion. So compared to chlorine, fluorine has a lesser electron affinity. So this is the difficult part here. Now I think that you all know the rest of the part. So which option is the
Ma'am,
right answer? Yeah,
ma'am, can you please explain the last part where you wrote the electronic configurations and how
yeah,
F is less than Cl?
yeah. So one second. Let me- Okay. So what is the electronic configuration of F? So 1s2, 2s2, it will be 2p5. Just one more electron and it is stable, right? So chlorine will be, it will be 3s2, 3p5. Bromine will be 4s2 and that all. So basically, if we add one electron, it is coming to this p, right? So we also know that the principal quantum number n, if you look at n, 2 and 3, then third shell will be much more larger than the second shell, right? Because the nucleus is here, and the distance between the between, if you look at the, actually the n is basically the size and the like how far the electron is away from the nucleus. So 3 means it is much more far away from the nucleus, which will make it more diffuse. The third shell is much more diffuse, which means it is much more bigger. The second shell is much more closer to the nucleus, so because of that it will be much more small. So if we add one more electron, in fluorine's case, the issue is that fluorine is already very small, and there are already 5 electrons here, and this 2p is also comparatively smaller, like to when we compare it to chlorine. So because of that, there will be so much electron repulsion. So if we add one more electron, this will be even more repulsion. There will be even more repulsion. Because of that, fluorine does not really like adding this electron. So in that case, if we compare with chlorine, chlorine will have higher electron affinity than fluorine, because electron affinity is essentially the energy released when we add an electron. Since fluorine does not like this additional electron, the energy released upon adding this electron will be less compared to chlorine. So that is the case for why chlorine has a higher electron affinity than fluorine. So is that clear?
Yes, ma'am.
Okay. So that is the difficult part here. So what about astatine, iodine, and bromine? What is the order for them? Can you please put it in the chat box?
Ma'am, option A.
Yeah, 1 second. Let me see in chat box. People are replying. Yeah,
Option B.
okay. Let us see. So already I said that. 1 second. So already we like clarified that chlorine will have higher, right? So it should be either this one or this one, right? Because here is the one F has lower electron affinity than chlorine, right? So now we have to look at this bromine, iodine, and astatine. So here the thing is that, as I said, whenever the size is increasing, the electron affinity will also increase. Like the energy required to, like energy release when adding an electron will also increase. No, I mean decrease. Right? 1 second. Yes, because why? If you look at, see, iodine and bromine, so iodine is much more larger than bromine. Why? Because iodine has so much other orbitals inside here, like d, f, and other, compared to bromine, so there will be so much shielding. Because of that, this nucleus cannot see this electron outside, the valence electrons. Because of that, this size of the element is much larger when compared to bromine. And if we add an electron here, essentially there is no where there is very less electron nucleus interaction. So if the electron cannot see the nucleus, then why will it come here, right? So the electron nucleus interaction is very less. Because of that, it also won't like to add electron here. Because of this, electron affinity will be very less. So is it clear?
Yes, ma'am.
Okay, so the order will be, the largest one will have the lowest electron affinity, then iodine, bromine, then as we said, fluorine, chlorine. So astatine is the largest one. So astatine will have the least electron affinity, followed by iodine, bromine, fluorine, and chlorine. Is it clear, or do you need, should I clarify anything?
No, ma'am, clear.
Okay. Anyways, I'll check the chat box also. Okay. So uh, those who answered like the other options, now you guys are clear, right? Okay. So moving on to next question. This is a very straightforward question. So according to modern periodic table, the physical and chemical properties of the element are periodic function of their what? Please put it in the chat box, the answer of this question. This we have learned from like class 8 or something. So I am sure that all of you know the answer. Yeah, right. So as you all said, it is option A, atomic number, right? Okay. So next question, all elements belonging to second period are. So before that, I just want to ask some straightforward questions. How many periods are there in the periodic table? And how many groups are there in the periodic table? Please put it in the chat box. The number of periods and groups in the periodic table. Yeah, please, when you write it in the chat box, please mention, yeah, how many periods, like 7 periods or 8 periods, then how many groups? How many groups? Yeah, 18 groups. Good, good. Okay. Okay, so as we know, we have like 7 periods, 1, 2, 3, 4, 5, 6, 7 periods, and 18 groups, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the question is about the second period. The second period is this one, right? Lithium, beryllium, boron, carbon, nitrogen, this group, this period. So the question is, to what category these elements are belonging to? Can you guys answer in chat box? So the second period elements belong to which category? Which option is the right answer? Yeah, right. So basically, the right answer is the normal elements, because let me just, I don't think it is required, but anyways, these are the transition elements, and these are the F block. This is the S block. This is the P block, and we were we were asked, is it halogens? Halogens is this fluorine, chlorine, this group. Then stable elements, because they are not definitely not stable element except for neon. The others are definitely reactive. For example, lithium is highly reactive. Then there is carbon, oxygen, fluorine. Fluorine is also very reactive. So definitely they are not stable elements and they are not transition elements. So basically they are just normal elements. So I assume there are no doubts in these third and fourth questions. If you have any doubts, you can just ask me now. Do you have any doubts? Okay. So I assume they do not have any doubts. We will move on to this question. So the correct order regarding the electronegativity of hybrid orbital of carbon. So to explain this, first we'll have to learn about something called the penetrative capacity. So this is a probability, like for plot against the distance from nucleus. So if this is the nucleus, for 1s we have the highest probability near the nucleus. For 2s we have, 2s is this green one. 2s we have a smaller probability here. Then there is a node. Then we have again here higher probability. For 2p here, I mean this is like closer to nucleus. Closer to nucleus we have very less probability and so on. So whenever we say that there is a high probability of finding an electron near the nucleus, it means that that particular orbital has more penetrative capacity. So in these, all of these three, 1s has the highest penetrative capacity because it has the maximum probability of finding an electron near the nucleus. And compared with 2s and 2p, 2s has the next penetrative capacity because near nucleus again we can find some kind of some electron compared to 2p. So because of this penetrative capacity, which it means that essentially if we put one electron in this 1s orbital, it means that the that electron is much closer to the nucleus, right? So if I put one electron in 1s and if I put one electron in 2p, it means that 1s electron is much closer to the nucleus and is experiencing much more electrostatic interaction. I mean the attraction is more compared to 2p. It means that electronegativity is high for 1s, right? Electronegativity is essentially what the ability of the nucleus to attract electron. So that ability will be much more if the electron is in 1s compared to 2p. So is this concept clear? Or do you have any doubts? Can you guys please respond? Should I check the chat
Yes,
box?
ma'am.
Okay, anyways, I'll check the chat box if you have any doubts. Okay. So if that is clear, then I'll move on to the next concept, the hybridized orbital. So sp, sp2, sp3 are all hybrid orbitals. And if we look at this s and p character, so essentially if we look at electronegativity, we have to look at the s character, because as we said, s orbital will have higher electronegativity compared to p. So if we have sp, we can, there is only two orbitals involved, s and p. So if we want to calculate what is the contribution of s orbital to this hybrid orbital, it is just 50%, right? 50% s, 50% p. So sp orbital has 50% s character, then 50% p character. So like that, sp2 will be having 1 by 3 s character and 2 by 3 percentage, 2 by 3 percentage P character. So this essentially will come around to 33 percentage or so. Then we have sp3. This is like 1 by 4 percentage of S character plus 3 by 4 percentage of P character. So this will be coming around 25%. Okay. So from this, I think it is clear which one will have more electronegativity. Can you put it in the chat box? Which option is the right one? Okay. Okay. Okay, so all of you have answered the right answer. It is option A. As we discussed, the SP have the highest S character, 50%, followed by 33% in SP2, followed by 25% SP3. So the higher electronegativity order, the electronegativity order is also the same thing, SP followed by SP2 followed by SP3. Everybody is clear with this question, right? Yeah,
Ma'am,
yeah.
ma'am, why we are not looking at the P1 because it is increasing for SP3, it is maximum at that point.
Yes, but it is max. One second. So your question is why we are not looking at the P contribution, right? So
Yes,
essentially, as I discussed here in this penetration property, S has more penetrative capacity. So even if it is like if we compare with 2s and 2p, still the S will be much more closer to the nucleus. So if we have more P character, it just means that the electron is somewhere here, but still it is not closer to nucleus, right? So essentially that is what, see, this hybridization is just mixing of s and p orbitals. So we have s orbital and p3, 3p orbitals here. But even if more p are there, still the probability of finding the electron from the in the 2p orbital is still like somewhat far away when we compare to 2s or 1s. So in that
okay.
case, again, anyways, 2p will be having, even if the number of p is high, it will be having lesser electronegativity. Is it clear?
Yes, ma'am.
Okay. So I'll move on to the next question. So this one, those who have attended the last session of mine, we have actually solved this question. Anyways, we'll solve it once again for those who do not attend. So which will be the correct electronic configuration for chromium? So here I'll give you two clues. The atomic number of chromium is 24. Then atomic number of argon is 18. Then I think neon is 10. So can you please put which option is right in the chat box? Okay. Okay, so everyone has answered it right. It is option B, this one, 3D5 for us one. So if anyone needs to explain, like anyone wants the explanation, please put it in chat box. I will explain. Otherwise, I'll just move on. If anyone wants the explanation, please put it in chat box. Okay, I think no one wants it, right? So then I'll go move on to the next question. Okay, so this is about Slater's rule. So before solving this, we will just look at what is actually Slater's rule. So here we discussed about the penetrative capacity and all those things. And here we discussed about where is it? Here we discussed about the how some screening is happening for this I mean larger elements like astatin, iodine, and all. So essentially, this Slater's rule is a set of rules to calculate the effective nuclear charge. So whenever we have some, one second, I'll just, okay. So we have an nucleus here. We have in like many number of orbitals and shells and all. So and there are electrons. So the nu- the interaction or the attraction felt by this electron with the nucleus is different than the interaction felt by this electron with the nucleus, because here this electron has to like these electrons are giving some kind of shielding to the nucleus. Because of that, this electron cannot really see this nucleus as effectively as this one. So, and if we compare it with this one, again, it has like all these electrons shielding it from the nucleus. So this one also sees lesser nucleus. See, I don't know if I am clear enough. Let me give you an example. So let's say if there is a principal here, or a class. Okay, that's a teacher here, and first row of students are sitting here. Then there is a second row, then there is a fourth row, and so on. So the teacher's direct attention will be to this first two students, and the second row students will have lesser attention because the teacher is much closer to the first row students. So essentially, because of these students, the teacher is not really seeing what all things these second row students are doing, right? So and third row students are much more safer because the teacher is much more far away from the third row, and the teacher cannot see what these people are doing and all those things. So essentially, this is the same that is happening for the nucleus case. So whenever there are some electrons in between, the nucleus cannot really see the outermost electron. This effect is called shielding. So to understand how much this shielding is happening and how much is the effective nuclear charge. Effective nuclear charge is the nuclear charge this electron is seeing after this shielding is happening. So that is Z star. So it is calculated by Z minus sigma. The sigma is the shielding constant. To calculate shielding constant, we have a set of rules. That is the Slater's rule. So am I clear?
Ma'am, a bit off.
What?
Ma'am, a bit not fully clear about
Okay,
this.
okay. So I'll explain once again. Maybe we'll go with the teacher student comparison. So we have a teacher here. We have like 3 rows of students. Some Okay. So the teacher is standing very close to the row 1. So the teacher can really see what these students are doing because the teacher is standing very close. And if but she can't really see what is happening in row 2 because it is much more far away, and these students can do pretty much anything. And if you really like imagine it how it is happening in real life, if these students are like sitting in like directly in front of these students, this essentially like the teacher cannot see these who all are sitting behind this first row, right? So like that, if you look at row 3, then this row 1 row 2 students are like almost covering this row 3 students, and this teacher cannot really see what row 3 students are doing, or what are they talking, or are they doing some mischievous things, all those things. So if we compare the same scenario to the nucleus is there, then we have a lot of orbitals, right? And we have electrons here, electrons. So the essentially the nucleus also can effectively see these electrons because there are no other electrons here, and there is no other repulsion or attraction. So this electron can definitely feel the full power of nucleus, but these electrons cannot really see because these electrons are kind of covering them from the nucleus's power. So the nucleus has lesser attraction with this now, and the power of nucleus felt by these electrons is less. That is the effective nuclear charge. Even though the nucleus is having, like say for example, nucleus's power is 6 plus, but this electron might not be feeling all those 6 plus because some of that 6 plus is cancelled by or neutralized by the negative charge of these two electrons. So that is called shielding. So essentially, these electrons might be feeling maybe 3 plus or 4 plus, depending upon how many electrons are there. So if you look at these electrons, one second, these electrons, again we have all these electrons shielding. So the power of nucleus is reducing here. Like the nucleus's charge is much more neutralized by the other electrons here. So the effective nuclear charge felt by this electron is much lesser. So that
Yes,
is,
ma'am.
yeah. So we are calculating the shielding constant sigma. So how much shielding is coming from these electrons. So for that we have this latest rule. Okay. So now we'll go on to what this later rule is. So if we have a configuration, say 1s2, 2s2, 2p6, and I want to know what is the effective nuclear charge felt by one electron in this p orbital. So already we have 6 electrons in p, but now we have to look at only one electron in the p orbital. So essentially this one electron it is interacting with the other 5 electrons in the p orbital, right? Then we have the 2 electrons from the 2s orbital, then again 2 electrons from the 1s orbital. So how these electrons are contributing to the shielding? For that we have to look at this shielding Slater's rule. So Slater's rule essentially says that whenever we are looking at S and P electrons, that is, if we want to calculate the effective nuclear charge for P or S electrons, then we have to follow this rule. This is like if the if the other electrons are in the same shell. For example, here if I'm looking at one electron 2p, I have to take the 2s and 2p together. This is the first shell. I mean the same shell, right? Like I'll, one second. I can say that this is nth shell because nth shell is where my electron is, and this is n minus one, n minus one shell, right? If we had something else, it will be n minus two, and so on. So if there are other electrons in the same shell as our electron is, then we have to take 0.35 for each electron. So in this case, I have 5 plus 2, 7 electrons in the same shell, that is 2, 2. So I have to take 7 into 0.35 for this nth shell. And for n minus 1 shell, I have to take 0.85 per each electron. So there are 2 electrons in 1s2, so 2 into 0.85. And if there was any n minus 2 the tooth shell, then the contribution will be 1 per each electron. And this is for d and f electrons. If I had, say if I had something like 3d5, and I want to look at what is the effective nuclear charge for an electron in D, then in that case, for the same shell, I'll take 0.35 per electron. And for other shells, that is n minus 1, n minus 2, n minus 3, I'll take 1. That is the Slater's rule. And if that's a special case, that is for oneness. If I am the electronic configuration is just 1s2, and in that case I want to calculate the effective nuclear charge for one electron in the 1s, then there is only one electron left, right? So 1 into 0.30. This is the special case for oneness. In other cases, for example, if it is 2s2 and I have to calculate the what is the contribution, it will be 1 into 0.35. Whenever there is, we are calculating the contribution from the same shell, it is 0.35, except for 1s2. If there are no other electrons and only electrons are in 1s2, in that case it will be 0.30. But in this case we have other electrons in 2s2, 2p and all, 2s and 2p, therefore we will consider 1s also in 0.35. But this is the case for helium when there is only 1s2 or 1s1, that is for hydrogen. So in these cases, if we have to look at the shielding constant, we will look at say that each electron will have zero point 0.3 contribution. So is this clear?
Ma'am, so only for hydrogen and helium will take it point 0.3, no?
Yeah, for only when this 1s1 1s2 happens, in that case we'll take 0.35. I mean point 3. In all other cases, even if 1s2 is there, it is 0.35. Yeah.
Okay.
So, but essentially we have to look at where our electron is interested, which electron are we interested. So if we are looking at, I am saying that I am looking only at this 1s2. So in that case, I don't have to look at these. This is because if my electron is already here, why I have to consider the electrons away from it, right? Because already the electron is here. So in that case, if you're looking at this, or everything on the right can be ignored. So in this case, again, we have to calculate, see, 1 into 0.30, because we are looking only at the S, right? Is it clear?
Yes.
Okay. So now we can solve this question. So the question is, which statement is incorrect about this latest rule? So I'll read out the options. An amount of 0.35 from each other electron within the same group, except for oneness group, where the other electron contributes only 0.30. So this is just how we explain now. If only if it is in oneness, and if we are looking at, if we are looking at oneness electron, then each will contribute 0.3. But for other cases, it will be 0.35. So is this right or wrong?
Right, ma'am.
Yeah, this is right. So we'll go to the next option. This is, if the group is of the NS-NP type, an amount of 0.85 from each electron with principal quantum number n minus 1, and an amount of 1 for each electron with principal quantum number n minus 2 or less. So as I already discussed, whenever it is n minus 1 or n minus 2, n minus 3, the contribution changes. For if it is s and p electrons, then the n minus 2 will be n minus 1 will be contributing 0.85 per electron, n minus 2, n minus 3 and other inner orbitals will be giving, inner shells will be giving 1 per electron. So this is also true. So third option is, if the group is of the D or F type, an amount of 1 for each electron closer to the nucleus than the group. So in the group, again, D and F electrons will be having 0.35 per electron, but everything else, n minus 1, n minus 2, n minus 3 and others inner orbitals will have just one electron per one electron contribution, right? So this
So,
third
ma'am,
option,
for rest of
yeah,
all those, like for only N shell, it will be 0.35. Otherwise, for
yes.
everyone, it is 1 only.
Yes, for D and F electrons. If our interest is D and F electrons, but if our interest is S and P electrons, then n minus 1 will have 0.85. In other cases, it is 1. Okay, so this is also true because for n minus 1, n minus 2, and other orbitals, it is 1. Contribution is 1. Then we have the fourth option, all electrons in the higher principal shell contribute 0.75 to the shielding constant. So this is the one which is false here because there is no 0.75 contribution in any of these cases, right? So the option 4 is the wrong option. So anyone has any doubts here? Let me see the chat box. Does anyone have any doubts? If you have, you can just put it in the chat box or you can ask me directly. Okay. So since no one has any doubts, we move on to next question. Okay, so this is a like practice problem for this Slater's rule. Calculate the effective nuclear charge for the 4s electron of Fe atom, which has the atomic number 26 in electronic configuration. This. So essentially, you have to calculate effective nuclear charge. The formula is Z star is equal to Z minus sigma. So sigma you have to calculate by Slater's rule. Z it is already given 26. So we will be calculating Z star. So I'll give you like 5 minutes to calculate and you can put it in the chat box. We are looking at this quantity, the Z star. So which option is the right option? You can put it in the chat box.
Ma'am, sigma
Yeah.
we will calculate according to the previous questions rule, na?
Yes, yes. These are the
Ma'am, for
Slater's rules. So
each that
always, yeah.
Ma'am, for each that we are adding for each shell, we'll add it up, na? For n minus one, then for
Yes,
n.
yes, yes. For each
Oh,
shell, we'll add it up. So I'll give you like 3-4 minutes, and uh, after you put the answer in the chat box, we'll discuss it. Please try to like put it in the chat box. Even if it is wrong, it is fine. We can still learn how to calculate it. Okay, but still we'll wait for like couple of minutes for others to also answer. Okay. Anyone else wants to answer, or shall I go for discussion?
I'm getting a entirely different answer.
Okay, so we'll discuss. So essentially, we are looking at this forest electron because the question is for forest electron, right? So we are looking only at forest electron. So 1 second. This is the nth shell, right? This is the nth shell, and this is the n minus one. This is n minus two. This is n minus three. So for one, we already have forest two. We are looking at one of the electrons. So there is one more electron left in forest. So 1 into 0.35, right? From 4s. This is the nth. Then n minus 1.
Ma'am, why did we took only 1 multiplied by
Uh,
0.35?
because there are 1 2 electrons, we are looking only at this electron, right? So this electron does not have any interaction with itself, right? It only interact with the other electron.
Yes.
Yeah, so we will only look at the other electron, not the same electron. That's why we are only taking one electron from each. Like if we are looking at 4s2, we'll take one electron. Then if you're looking at 3d6, we'll take one electron. The rest, it will be interacting with the rest of the 5 electrons, right?
Okay.
So when we have the n minus 1 shell. So we have how many electrons in the n minus 1 shell? So there is 2 from S, then 6 from P, then another 6 from D, right? Into 0.85, right? This is what we saw here, 0.85 for n minus 1. And we are following this rule because we are looking at S electrons. Then we have n minus 2. For n minus 2, how many electrons are there? 2 from S, then 6 from P into 1, right? So n minus 2 was 1, contribution was 1. Then the all the other shells, that is n minus 3 and all others, it will be 1. So there are 2 electrons, so 2 into 1. So if I calculate, let me calculate. So this is 0.35, this is 2 plus 6 plus 6, 14 into 0.85 is 11.9. Then there is 8 here, so 8 into 1 is 8. This is 2. So if we add up 0.35 plus 11.9 plus 8 plus 2 comes around, it is so the sigma is 22.25. Is this clear? Do you guys have any doubts in calculating sigma?
No, ma'am.
Okay. So
No, ma'am.
okay, so sigma is 22.25. So now this is pretty now it is pretty straightforward because the uh, equation is just here. So z star is equal to, z is already given, 26. 26 minus 22.25, which is equal to minus 22.25, 3.75. So option A, right? So this is option A. So is it clear? I'll give you one more example. Now, calculate the effective nuclear charge for the 2p electron of F atom. So here I have only given the atomic number. You guys have to write the electronic configuration, then solve for sigma. Then you have to write it in the chat. Write in the chat box what is the effective nuclear charge. I'll give you a couple of minutes. Okay. Okay, one more minute and then I'll discuss. Okay. Yeah, someone has raised a hand. Yeah. If you have any question, you can ask. Hello? Okay. Maybe by mistake. Hmm. Am I audible? I think my browser has some issue.
Yes, ma'am, you are audible.
Okay. So we will solve the question then. So the atomic number of F is 9. So first we'll write the electron configuration. 1s2, 2s2, 2p, 5, right? Okay. So now we have to look at what is the effective nuclear charge for the 2p electron. So this is the uh, nth shell. This is the n minus 1th shell, right? So now I don't have to, so from P I'll have 4, right? 4 plus 2 from 2s, so 4 plus 2 into 0.35 because it is from nth shell. Also we are looking at the p electrons. Then we have the n minus 1, so we have 2 electrons from 1s into 1, not 1
Ma'am, why
point.
we didn't took one electron? Why did we took four electrons?
Yeah, which time? Hello, am I audible? Hello, hello.
The reason why we have taken 4 plus 2.
Yeah,
But
sorry.
earlier we were taking one electron, so why did we took four electrons this time?
One second. So what is the question? One second. Actually, I was disconnected. Yeah.
Ma'am, actually I was asking that why did we took four electrons? Because in earlier cases we were taking one only, no? For the 2p.
That was
Here,
S2, S2, plus
yeah,
2.
it was S2. See, here we were looking at the S2, right? This was the nth. So already one electron we are looking at. So the only one electron is left, right? See here, two electrons are there. So we'll only look at the one electron, remaining one electron. Here the question is 2s2 2p5. So I am interested in this p one electron from the p orbital. So how many are left in the p? Four, right? That's why we are taking
Okay.
four here. Is it clear now?
Yes, ma'am.
Okay. So essentially this is 4 plus 2 into 0.35 because it is the nth shell. Then from n minus 1 we have 0.85 from this, and we are looking at S and P. So essentially the answer here is, one second. So we have 6 into 0.35. which is 2.1. Then we have 2 into 0.85. 1.7. So essentially
Where
sigma
is the
is,
one?
yeah,
Where is the one?
there is no one, right? See here, okay, my cursor is not visible. See here, there is nothing else here, right? There is no n minus 2 orbitals or shells. This is 1 s 2. Before, beyond that, there is nothing else, right? So there is no n minus 2 or n minus 3 shell. So we don't have to take that contribution, right?
Okay.
Yeah. So sigma here is 2.1 plus 1.7, which is equal to 3.8. So z star is equal to z minus sigma, which is equal to 9 minus 3.8. So 9 minus 3.8 is what? 5.2. Okay, did I stop sharing? One second. So the answer is 5.2. Z star is 5.2. Is it clear?
Yes, ma'am.
Okay. So there is one more question. This is the electronic configuration of selenium, and this is the I have given the electronic configuration. Now the chosen orbital is highlighted. So I want to look at what is the contribution of these p electrons. I mean, not contribution. What is the effective nuclear charge felt by an electron in this 3p? So I'll give you the atomic number of selenium. Selenium is 34. Can you guys please solve it? I'll put it in chat box. Z is 34. So what is Z star for an electron in 3p? I'll give you a couple of minutes to solve. Okay. Anyone else wants to answer it?
Ma'am,
Just a
please wait.
Yeah, okay. Okay.
Yes, ma'am.
Okay. Can you put it in? Okay, okay, okay. So let's discuss now. So we are looking at this 3p. So we don't have to look at the other things, right? These things are not, we don't want that, because we always look at n minus 1, n minus 2, and all. Now everything on the right side is ignored, because they do not contribute in the shielding, right, for this 3p. Now we will calculate. Okay, I'm not able to see the cursor. Okay, so we are looking at 3p, this electron, in the electron in this orbital. So we have 3s2, 3p are the end shell. Then 2s2, 2p6 is in the n minus 1. Then 1s2 is the n minus 2, right? So if we calculate, we have 2 plus 5 into, okay, 1 second. Okay, okay. 2 plus 5 into 0.35, then 2 plus 6 into 0.85, then 2 into 1. Is this clear how I have taken it? Is it clear?
Yes, ma'am.
Okay, so values will be 2 plus 5, 7 into 0.35, which is equal to 2.45 plus,
7.5.
huh? 1 second. 7 into 0.35, 2.45, right? Then 2 plus 6, 8. 8 into 0.85, 6.8, then 2. So 2.45 plus 6.8 plus 2 is 11.25. So Z star is Z minus sigma. So Z is, as I said, 24. 24 minus 11.25 is equal to 12.75. Am I right? Did I make any calculation mistakes?
Z is 34.
Okay, sorry, 34. 34 minus 11.25 is 22.75. Thank you. 22.75. Is it clear?
Why?
Yeah, actually, I can't hear you properly. Can you put it in chat box? Hello? I'm sorry, actually, again I was kicked out. Was anyone asking any question? Is my screen visible?
Yes, it.
Okay, so no one has any doubts here, right? Shall I move on?
Yeah.
Okay. So this is again a straightforward question. Which one will be the correct increasing order of effective nuclear charge among the following levels? So this one you don't have to really solve for effective nuclear charge and all. This from the general knowledge from all this from
Yeah,
the.
no.
So someone is speaking, but I'm not able to hear properly. Selenium is 34. Sorry, selenium is 34. I had written in the slide is 34, but when I calculated, I accidentally did it as 24, but selenium is 34. Okay. So again, you don't have to. 1 second. So you don't have to calculate the effective nuclear charge and all here. Uh, Essentially, you just have to arrange this in a particular order. So you know that all these elements belong to the which period? Let me just show you the periodic table. Which period does it belong to? All the C, N, O, F, N, E.
P.
Second period, right? So this belongs to second period. So if we write it in the order of increasing atomic number, which is C, N, O, F, N, E, right? So from the C to Ne, the atomic size is decreasing. Ne is the smallest here, carbon is the largest here in these elements, right? So we already know that when does this so why does this size is decreasing? Why is the size decreasing from left to right, from carbon to neon? The reason is there is only one shell here, two. So we have 2s and 2p here, and all the electrons are added to this 2s 2p. So carbon is 2s to 2p2, nitrogen is 2s to 2p3, and so on, and neon will be 2s to 2p6. So the extra electron is added to the same shell, and at the same so because of that the number of shells are not increasing. Because of that the size is not increasing, but what happens is the nuclear charge is increasing. So carbon's nuclear charge, the normal nuclear charge is 6, then 7 is for nitrogen, and so on, 8, 9, and 10. So neon will have the highest atomic charge, atomic number, right? 10. So because of that, what happens? Even though the number of shells is the same, the atomic charge is increasing, which means that now the nucleus has much more power to attract the last electron, right? When going from carbon to neo. Because of this much more increased attraction, the size of the atom will reduce. That means because of the nucleus electron interaction, this electron is much more pulled close towards the nucleus. Because of this these elements are contracted from going from carbon to neon. So in because of that, the size is decreasing. So now I have told you all the reasons why the size is decreasing, and in during that I have also told who has the highest nuclear charge, right? So now can you solve for this question? Which is the right option? Okay. Okay. So so from carbon to Ne, the nuclear charge is increasing, and the number of electrons is also increasing, but the size of the shell is the same. and because of this nuclear charge is increasing, the electrons are much more pulled towards it, which means that the effective nuclear charge is also increasing in this order, right? Which means that neon has the highest effective nuclear charge, then followed by fluorine, oxygen, etc. So the option B will be the right answer. I can't see my cursor. Option B is the right answer. Is it clear?
Yeah.
Okay. So moving on to the next, before moving on to the next question, I just want to give you an overview about ligands. And last class also we discussed. So there are like different for the when a complex is formed, the ligands is basically an electron donor, right? So the ligands can be of two types. And ligands can be classified based on many types. So it can be based on the type of donor atom. The donor atom is neutral or ionic in nature, or sigma donor, or pi donor, or pi acceptor. And then how many donor atoms are binding to the metal, etc. So the neutral, the sigma donor, for that one example would be, NH3. So we have NH3 with lone pair. So from this lone pairs will be given to the metal. And this NH3 is also a neutral ligand. At the same time, it is a sigma donor ligand also. Then for pi donor, an example would be Cl minus. It is a ionic ligand. At the same time, it's a pi donor ligand also. For pi acceptor, carbon monoxide is a good example, and it is also a neutral ligand, but at the same time, it's a pi accepting in nature. So, and this question also we discussed last class, where we were talking about this C2O4. C2O4 is also known as oxalate. So each oxalate has two donor atoms. See, here we have two oxygens here, right? So each oxygen, this is the oxalate group. So each oxalate is having two oxygens. So the density is 2. So this is a bidended ligand. And so through both oxygens, it is binding. So these informations will be utilized in the next question. The total number of geometrical isomers for the complex ion. The complex is given here. Before solving, I'll just give one some brief overview about what are these geometrical isomers. So geometrical isomers are either cis trans isomers. So it is normally seen for square planar complexes, that is when all the ligands are in the same plane. For example, for this, I'm just giving some random example. So this is a square planar complex. So in this case, we don't have any geometrical isomers because all ligands are the same. But what if I have something like this? A, B, B, A. Then M, A, A, B, B. So here this is a cis isomer and this is a trans isomer. So trans essentially means opposite to each other. So here we have each ligand opposite to each other. So that's a trans. Then this is cis means essentially near to each other. So on the side, so these are like near or on the side. So this is a cis isomer. Now this is a before going on to the question, you also have to look at what is the coordination number. Then only we can go to this. So the coordination number is essentially how many donor atoms or how many donor atoms are surrounding the metal. So here we have H2O, two H2O are there, and one oxalate is there, then one bromine, one chlorine. So what is the coordination number of this complex? Can you please put it in the chat box? Oh, oh, I'm sorry. Actually, I did not see the chat box. Hmm. I'll just go through the same thing once again. One second. Uh,
Are you able to hear me now?
Yeah, I can hear like, but your voice is actually breaking down. But I'll just go through the question, that same question once again. This was the one we already discussed. This is clear for you, right?
Ma'am, I had a doubt in this one,
Hmm.
whether the atomic number is 34 or 24.
34, 34. See, I'll show you the
So, ma'am,
periodic
the
table
answer
as
for
well.
Z star will be 22.75 or 12.75.
No, it is 22.75. I have like shown here 22.75. I did not write it, but the answer is 22.75. Z star is 34 minus 7.25, which is 22.75.
Okay.
So yeah, so this one was like which is the increasing order of effective nuclear charge. So from this is the second period elements, and if we arrange it in order of like atomic number, it is C N O F N E. And if we go from carbon to neon, the number of or shells is not increasing. It is essentially 2s 2p for all, but we are adding more electrons to it. And the nucleus is also gaining more charge, right? Because for carbon it is 6, for nitrogen it is 7, oxygen it is 8, and so on. So the nuclear charge is also increasing, the number of electrons is also increasing. So nucleus can much more attract the electron, much more strongly in neon when we compare to carbon. Because of because of this higher interaction, the atom will contract, which means that size will decrease. So from carbon to neon, the size is decreasing. Because why? Because the nuclear charge is also increasing from carbon to neon. So if you look at the effective nuclear charge, it is also increasing from carbon to neon, because effective nuclear charge and the normal nuclear charge, the effective nuclear charge is increasing because there is no more other shells are not coming in, right? The screening is the same for all, just other one or two electrons are coming in. That screening is comparatively less. And also but at the same time, the nuclear charge is also increasing, which means that the effective nuclear charge is also increasing. Is it clear? So from that we can say that from carbon to neon, this is the option. Like which option? This one, option B, CNOFNE. Ne will be having the highest effective nuclear charge. Is it clear? Maybe she got disconnected again. Okay, anyways, we'll discuss the next question. Okay, 4CN, 6CN. Okay, okay, so here we have H2O. H2O will be bonding through this oxygen. So we have two H2O. So there'll be from H2O's the coordination number is 2. Then oxalate, as I said from here, each oxalate is having two oxygen donors. So oxalate is also giving 2. Then there is bromine and chlorine, each is giving 1. So essentially the coordination number is 6. 2 plus 2, 4 plus 2, 6. Okay, is it clear? Am I audible?
Yeah.
Okay.
Yes, ma'am.
Okay, okay. So the coordination number here is 6. So this is an octahedral complex, right? So I can, for octahedral complex, we have similar this trans-cis combinations like I have shown here in the picture. So either it can be, this cis or facial isomer. That is cis in the sense these are like to the on the side, and it can be trans also, like on the opposite side. So for the octahedral complexes, many isomers are possible. We can also define on the basis of this chlorine itself. Like if I have, like, let me give an example. So if I have say FMA A, B, 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 B. This is also a trans. This is also a trans isomer, octahedral for octahedral complex. Then I have M, B, A, B.
Ma'am, am I audible?
Yeah, now you're audible. Sorry. Yeah, I think you were disconnected in between. Maybe we can discuss at the end that question.
Yes, ma'am.
Okay.
Ma'am, can you please explain this once again? Then previous is only one left, I guess.
Yeah. So this is we are looking at how many geometrical isomers we have for this complex. So before that, I just explained geometrical isomers are possible for this square planar complexes and octahedral complexes generally, and this MCl, this one is a this is for square planar complex, and you can have cis and trans. Like for example, okay, I don't have that. Okay, if I have M A A B B. This is a cis isomer because these A are closer to each other. Then I can have M A, not this, M A B B. So this is opposite to each other. So this is a trans isomer. So this is for square planar complex. And now then we looked at what is the coordination number for this complex. So this is we have two from water, two from oxalate, because here as I showed oxalate is giving, each oxalate will have two oxygen as the donor atoms. So coordination number for oxalate is 2. Then for bromine and chlorine, we have one each. So coordination number is 6 for this complex, which means that it is an octahedral complex. So octahedral complex can have this facial isomer, meridional isomer kind of isomers, geometrical isomers, where these are like closer to each other, or at least one pair is trans to each other. These are also called cis or trans, but when there are like three ligands like this, it is not directly, we cannot directly call it cis or trans, because these are also cis. Here we can consider these are also cis, but we can say that whenever it is meridional or trans, at least one pair will be opposite to each other. So in that way we can identify it as facial or meridional isomer. And another case is here when we have uh, 2A and 4B. This is also B, 4B ligands. Then we can have A trans to each other or A cis to each other. And here we say that this is a cis and trans isomers with respect to ligand A, because here A is the because we can write it with respect to B as well. So we can say that this set of isomers is with respect to A. This is trans with respect to A. This is cis with respect to A. So in this question we have to find out what is the number of geometrical isomers. So I'll just show the solution, because this is not I cannot write it on the slide. So we have four options, like four geometrical isomers are possible for this complex, because it is either water in the trans, this is with respect to water it is trans, or with respect to water it is cis. See, with respect to water trans or with respect to water cis. So this is one set. Another set will be the with respect to water bromine is cis, with respect to water chlorine is cis, like that. With respect to water, chlorine and bromine are cis, and with respect to this water, we have chlorine and oxygen as cis. In this case, we have bromine and oxygen, and here it is the same. So, with respect to this water, the isomer state, chlorine and oxygen, bromine and oxygen. So there is four isomers possible, for four geometrical isomers possible for this complex. Is it clear?
Yes, ma'am.
Okay. So this is a pretty straightforward question. In which of the following nickel is in the highest oxidation state? So you guys have to calculate the oxidation state for each, and you should tell me which one has the highest oxidation state. I'll just give you a couple of minutes. You have to put it in the chat box. Okay, maybe we can step by step we can go. For the first option, what is the oxidation state? For K4 nickel CN, what is the oxidation state for it? K4 nickel CN6. Okay, we'll solve and then we'll just go to the next. So K4 is just to balance the counter, balance the counter ion. So K4 means it is 4 plus. So it means that nickel CN6 is 4 minus, right? That's how this it is balancing the charges. So nickel, we don't know the oxidation state of nickel, so we'll just give X for that, X plus. Then Cn is a like ionic ligand, each Cn will give minus 1. So 6 into minus 1 is equal to minus 4. So x minus 6 is equal to minus 4. X is equal to minus 4 plus 6, which is plus 2. Right? So the oxidation state of nickel in this case is plus 2. Is it clear? I hope it is clear.
Yes,
Then,
ma'am.
yeah, then, so we'll just write. So option A is nickel is in plus 2. I'll wait for others to find out what is the oxidation state for option B. Let me see. Option B, okay.
Can you explain it again?
Yeah. So we have, okay, nickel, 1 second. So what is essentially a complex? The complex is essentially the only things which is inside the square bracket. So nickel CN6 is the complex, but this K4 is there to balance the charges. If you remove this K4, what will be there? Each K is giving one plus charge. So if you remove 4 plus, 4 minus will be remaining here, right? So it is, so we can write just the complex as NiCN6 4 minus, right? So now we need to calculate the oxidation state of nickel. We don't know the oxidation state of nickel, so we'll just keep it as X. Then for each CN is a charged species, so each CN has one negative charge, right? And we have 6 CN. So 6 into minus 1, and it is equal to the total charge on the complex is 4 minus. So x minus 6 is equal to minus 4, then x is equal to plus 2. Now is it clear?
Yeah, clear.
Okay. So we'll go to the next option B. Yeah. So again here also it is NiF6 2 minus, because K2 is outside and overall charge on the complex is 2 minus. So again we don't know the oxidation state of nickel, so we'll just keep it as X. Then F is F minus, actually not the neutral form. F, each F will have minus 1 charge, so 6 into minus 1 is equal to minus 2. So X minus 1 is equal to minus 2. So X is equal to plus 4, right?
Yeah, here every point the number of every element it taken as -1.
No, it depends on what the element is. So if for the example, 1 second. For the example, carbon monoxide. Carbon monoxide is a neutral ligand. So here I was explaining, right, the neutral ionic sigma or something. So for all the neutral ligands will be having zero oxidation state because they are in the neutral ground state, and the ionic ligands will be having depending on what ion it is, the charge. So Cl bromine F will have -1. Then for example, if there is a ligand called O2 2 minus or O2 minus, then the charge will be 2 minus, right? If, yeah. So again, this is X is equal to plus 4. So what is the oxidation state of nickel in this complex? As I said, carbon monoxide is neutral here. So what is the oxidation state for nickel here? Please put it in the
If it
chat box. Yeah, you are asking something? So as everyone said, it is 0, because as I said here, again, there is no charge on the complex, so X is for nickel, X plus 0 into 4, because the charge on this CO is 0, is equal to 0. So X is 0. So nickel is in its neutral state here, right? So the option D, what about option D? What is the oxidation state of nickel in option D? Okay. So option D, again the charge on the complex is -2. So X plus -4, I mean not -4, 4 into -1 is equal to -2, because each Cn is giving -1. So X minus 4 is equal to -2 and X is equal to +2. Clear? So from this, all the calculations we came to know that which one has the highest oxidation state? Option B, right? Because option A was nickel was in 2 plus state, then option B is +4 state, then option C nickel is in 0 state, then option D nickel is in +2 state. So option B is the right answer here. Am I clear here?
Yes, ma'am.
Okay. So this is just to give an idea of how many electrons are there in each metal d orbital when they are in the +2 oxidation state. So if you really know the transition elements in the right order, at least the 3D, from scandium to zinc, and what is the number of electrons in the +2 oxidation state, you can just count on your finger actually, if you know the first two elements. So it is like scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, nickel, copper, zinc. So from your fingers, you can just say, okay, what if someone asks, what is the number of electrons of vanadium in its plus two state? So I know that scandium, titanium, vanadium. So in +2 state, it has 3 electrons. See, 3 electrons. So if you just learn this, it will be much more easier and helpful for you to solve many questions. Otherwise, you'll have to, think about what is the atomic number, how many electrons are removed, all those things. So from this, you can easily like find out what is the number of electrons in its +0 state, in its 0 state, or +4 state, +6 state, anything, right? So at least the 3D elements, if you can learn, it will be very helpful. So again, this question we can solve. Then we'll go to why the 18 electron rule is important, and who all follow 18 electron rule. So this one again, among the following, which one is paramagnetic? Here you have to know what kind of ligands these are. So for that, we have the spectrochemical series. This is a series or an arrangement of ligands on the base of experiment. So from experiment, they found that this is a particular order of ligands, and in this order, this kind of if we like each if we arrange the ligands in this order, we can see that a particular pattern of electron filling is happening in the complexes. This is according to the crystal field splitting theory or the ligand field splitting theory. As I know that you guys have studied this in the week 2, I think. So the weak field ligands, generally, if we have the weak field ligands like I minus or S2 minus or Cl minus, then the electron pairing will not happen. All the T2G and EG levels will be singly filled. And if we go for this strong field like PPH3, Cn minus, Cu and all, the electrons will be first paired, then it will be going to the EG. So I'll just solve one for you and then we'll solve together. Okay, so for cobalt, this cobalt, first we have to look at the oxidation state of the cobalt. So again, X plus the NH3 is neutral here, so 0 into 6. Then we have the overall charge 3 plus, so X is 3 plus, right? So cobalt is in 3 plus state here. So cobalt in its +2 state has D7 electron, as I showed here. See, cobalt has D7. One second. Someone is joining. Yeah. So cobalt in its plus 2 state has d7 electron. So plus 3 means what? If I remove one more electron, it will be in plus 3 state. So how many number of electrons will be there in D? It will be d6, right? Is it clear?
Yes, ma'am.
Yeah. So the cobalt 3 plus is having d6 electrons, and NH3 is a what kind of ligand? NH3 is like a medium kind of ligand. It is not weak field and it's not a strong field also. So for 3D elements, 3D transition elements, we generally consider even if NH3 is here, we will consider it as a weak ligand. But if it is 4D or 5D elements, transition elements, then we have to consider it as a strong field. So here we have P2G and EG, and also while drawing this we have to look at what is the coordination number. So here the coordination number is 6, it is an octahedral ligand. So we have P2G EG splitting, right? So and it is a weak field ligand, so we have to first singly occupy, then pairing will happen. 5, 6. So this is definitely paramagnetic, right? Paramagnetic means the number of there is at least one unpaired electron, right?
Ma'am, is this
Yeah.
a thing that the carbon and nitrogen bonded elements are strong ligands?
No. This, if you look at here, one second. Here, this iodine, bromine, here, these all are pi donor ligands. See, here I showed you just there can be sigma donor from the sigma, then there can be pi donor and pi acceptor. So generally we see that the pi donors are the weak ligands, and then followed by sigma like H2O, CH3C and NH3. These are sigma donor ligands. And then this CO, and CO is a strong pi acceptor ligand. So in basically this weak field strong field is coming from the interaction of the ligands with the metal, and generally we see that the pi donor ligands interact much lesser with the metal compared to the pi acceptor. So that will be much more clear when I explain the molecular orbital diagram. So after we finish this question we will just go through this. Okay, so
Okay, ma'am.
yeah, so this definitely is a first option is definitely paramagnetic in nature. Now we'll go look at the second one. So in second one is also what is the okay. You guys have to tell me what is the uh, oxidation state of nickel in option B.
2 plus 2.
2 plus. Okay, 1 second. Yeah. So we have x plus then 4 into minus 1, because each fluorine is giving minus 1 and overall charge is minus 2. So x minus 4 is equal to minus 2. Sorry, minus 2. So x is equal to plus 2. You are right. So nickel is in plus 2 state, and as I said, nickel in plus 2 state will have B8. See, B8. The pointer.
Ma'am,
Yeah.
I have a question.
Hmm.
Ma'am, for Balt in plus three state,
Hmm.
right? So most of the in cobalt plus three state, uh, NH3 act as a strong field ligand. Pairing occurs there.
Huh. Um. Yeah, maybe it is true. I don't actually. I'm not sure about it. Yeah, because whenever the metal is in a higher oxidation state, then it can act as a strong field again. That the first one I'll check. The next class I'll check and tell you. At least the rest of the ones, I think we are sure about it. So first one I'll check and I'll tell you in the next class. Thank you for noticing. So what was I telling? Yeah. So nickel is in plus 2 state here. The number of electrons in D is 8, as I showed here. Nickel in plus 2 state has D8 electrons. Then if it and now you have to look at the coordination number. It is 4, so it can be tetrahedral or square planar. Normally for 3D elements it is square. It is tetrahedral, but one exception is nickel CN4. In that case, it will be square planar. So here this is nickel Cl4. It is definitely tetrahedral. So Eg level, E level will come first, then T2. So again, this is a weak field again. So first we will singly occupy, then we will pair. So 1, 2, 3, 4, 5, 6, 7, 8. So this is also paramagnetic in nature, right? Is it clear?
Clear.
Okay. So yeah. So what about the oxidation state of Fe in option C?
Plus
Again,
2.
Yeah, plus 2, right? Do I have to solve it?
no, it's okay.
No, ma'am.
No, ma'am.
Okay, okay. So Fe in plus 2 state has d6 electron, as I showed here. Fe ruthenium osmium in plus 2 state has d6 electron. So T6, and also it is a octahedral complex. So definitely T2G, Eg, and Cn is a strong field, as I have shown here. So first pairing will occur, then it will go. First pair will occur in the T2G, then it will go to Eg. So first 1, 2, 3, 4, 5, 6. So there is no unpaired electron in FeCN6, 4 minus. What about the oxidation state in nickel in the last option?
4 plus 4.
Yeah, so I'll just solve NiF6, 2 minus. So x minus 6 is equal to minus 2, x is equal to plus 4. Yes. So this is also a weak field ligand. So and it is octahedral in nature. So definitely T2G Eg is there. So first it will be singly occupied. Also this is nickel in plus 4 state, right? So nickel in plus 2 state is D8. So plus 4 means what? We have to remove 2 more electrons. So it will be D6, right? So 6 electrons will be there. So 1, 2, 3, 4, 5, 6. So definitely this is also paramagnetic, unpaired electron is there. So the first option I will check and tell you in the next class. For the other options, except for FeCN6 4 minus, other two are paramagnetic in nature. Is it clear?
Ma'am,
Right.
so in this question, two of them are paramagnetic, right?
Yeah.
NiCl4 and FeCN also.
No, NiCl4 and NiF6. Option B and option D are paramagnetic in nature. FeCN6,
Yeah, yeah,
as I
sorry.
showed here, it is diamagnetic.
Yes,
But
ma'am.
yeah, it's asked that what is one is paramagnetic. Is it any concentration of ions or atomic to be said?
Uh, that I did not understand.
Should we elect any one from them?
No, no, no. Like whenever, even though the question is asking just which one, most of the time, sometimes it can be like all can be paramagnetic. Sometimes only one can be paramagnetic. You always have to, solve it and then you have to answer. Right? No, not all questions are single answer type questions. Sometimes it is multiple answer type questions also. Okay.
Okay. So there is a question for that. As we know, ligands is the electron donor. So can we say that it is ion donor?
Um. Yeah. Like the metal is forming different kinds of bonds here. So it can be if it is like a uh, ion interaction, it can be an electrostatic interaction also, right? So in that case we can say, but in cases like CO and all carbon monoxide, it there are no unpaired electron. There is no like it is not giving anything. It is actually taking from the metal. That's why it's a pi acceptor, right? Like this.
Okay.
So there are the ligands can be ionic or neutral. It does not matter. It just has to have a donor atom which has a lone pair or which has an extra ionic charge, like negative charge, or at least a an empty pi orbital.
Okay.
Ma'am, among the four options, now we are discussing through this, two is the answer no.
Yes.
Among the four options,
Hmm.
two options are the right answers. How
Yes.
can we choose? If
Then
we can choose any
no,
one
we can
among.
most of the time we can.
Hmm.
It is not restricted to one option. You can just put
Hmm.
both,
Hmm.
right? It will be right. Sometimes if you don't answer both, they won't give marks also. So that's why you have to solve all the options and then you have to mark accordingly.
Okay, ma'am. Thank you.
Uh, So now we will discuss why some complexes follow 18 electron rule, some does not. So uh, this is for weak ligands like pi sigma orbital sigma donated ligands or pi donated ligands. So in that case, these ligand orbitals and the metal orbitals interact and several molecular orbitals are formed. This is there are like six molecular orbitals here, and this each can take up how each orbital can take up maximum of 2 electrons. So 6 into 2, 12 electrons can be accumulated here. Now the d orbitals is splitted into T2g and Eg star. So here I am only talking about the octahedral splitting. So we have T2g and Eg star. So in the weak field ligand case, the T2g is a non-bonding orbital. It does not have any contribution from the ligand. It is purely a metal orbital, and at the same time, the Eg is a anti-bonding orbital. That's why it is Eg star. So we all know that whenever some electron is present in the antibonding orbital, it is not that much stable, right? But in this case, this splitting is very less. This splitting between T2g and this Eg star is very less. It means that this Eg star is not that much antibonding in nature. It is antibonding, but weakly antibonding, right? So if there are some electrons, if some electrons come in here, it does not matter that much because it is weakly antibonding in nature. So if what let's say that I have filled all the electrons here, so 6 into 2, 12 electrons, and here we have 3 orbitals, so I am filling 2 electrons each. So again we have 3 into 2, 6 electrons here, and here we have 2 orbitals. Again I am filling 2 each. So again 4 electrons are coming. So total it will come around 12 plus 6, 18 plus 4, 22. Right, so the maximum number of electrons this can go up to 22, and some or complexes have 21, some have 20, because some electrons are not filling here. Here this is allowed because this Eg star is weakly antibonding in nature. It does not matter because it is weakly antibonding in nature. This is what happens for this weak field ligands like I minus, Br minus, etc., like these weak field ligands. So this I have considered only the sigma orbitals of the ligands. In this I have considered the pi orbitals also. So in this case, also like if the essentially if the interaction is less, the interaction of the ligand orbitals with the metal orbitals is less, then this gap will be less. If the gap is less, then this Eg star will be weakly antibonding in nature. If it is weakly antibonding in nature, it does not matter if we have electrons there. But whenever the interaction of ligands with metal is much more, that is if we when we go from here to here, let's say it is NH3 or En or bipyridine, in these cases what happens is this interaction is much more. Because of that this splitting is much more. So now the Eg star is uh, the antibonding character of Eg star is increased. Now if we keep an electron here, it may not be that much stable compared to this case. So here also it is possible, but it does not prefer that much. So whenever we have some kind of like intermediate ligands or strong field ligands, not carbon monoxide alone, sometimes like maybe NH3 En alone, this kind of thing is happening. The Eg star is becoming more and more antibonding in nature, and when the antibonding nature increases, it does not like electron coming here. So essentially the electrons will be only here. So it will be 12 plus 6, 18 electrons. But it can be lesser than 18 or it can be more than 18 also, because T2G is still non-bonding in nature. So non-bonding does not have to be filled all the time because it does not interact with any other, right? So it can be maximum, it can be 18 or less than 18. So
Ma'am,
yeah,
ma'am, I did not got these two diagrams very clear.
okay. So once again I'll explain. So these are the orbitals of metals. These are the ligand orbitals. Whenever the metal and ligand interact, some kind of mixing is happening with these two or this metal and ligand orbitals, and that's
Yes.
where we are getting the molecular orbitals. These are the molecular orbitals, right?
Okay.
So here, another thing is that metal has atomic orbitals. The ligand most of the time has a molecular orbital because ligand has multiple atoms. So I am not including that complexity here. You just have to think that the metal and ligands are interacting, and due to that, some kind of molecular orbitals are forming. So the character of each molecular orbital is different. So if you look here, this one, this T2G level, it has only contribution from metal because see this line, this is directly from metal. It means that this is a non-bonding molecular orbital. It does not have any contribution from the orbital from the ligand. This is purely a metal d orbital, but all of these are in the same energy degenerate. That's why we see in a T2G we have three degenerate orbitals. That's
Yes.
what it is shown here. So these orbitals are due to the interactions of the np or ns orbitals of the metal with the ligand orbitals, and we have some bonding set here. So there are like 6 orbitals here. So each orbital can accommodate how many electrons? 2. So 6 into 2, 12
But what are
electrons.
the base orbitals where you have written A1, G, EG, and TR
These
only?
T1, A1 all denote to the symmetry of the orbital. That is not related to your course right now. This is some advanced course content. Like each orbital have a certain symmetry where each lobe is located. Is it symmetrical? Is it anti-symmetrical? All those things. So that is not required right now. So this class I won't be going through. If it is required in future, maybe sometime we can discuss. Each orbital will have it can take 2 electrons. So 6 orbitals are here. 6 into 2, 12 electrons can be accumulated here at the max. Then this T2G is non-bonding in nature, and there we have three T2G levels. So each T2G orbital can accommodate 2 electrons. So 3 into 2, 6 electrons can be accommodated at the max here. But the thing to note here is it is a non-bonding orbital. It is not interacting with the with the ligand. So it is not necessary that we have to fully fill the T2G orbital. It is fine if we have 2 electrons also, it is fine. And whenever, and this EG star, this is an antibonding orbital due to the interaction between the metal and ligand. So EG star is also like a degenerate. There are two EG levels, but the nature of that EG levels is that they are antibonding in nature. So whenever we have some electrons in the antibonding molecular orbital, it is not that much stable, right? So, but in this case, the difference between this T2G and EG splitting is very less, which means that this EG star is not that much strongly antibonding. This is said to be a weakly antibonding character. Since it is weakly antibonding, even if there are electrons in it, it does not matter much. It does not affect its stability that much. So in that case, we can add electrons here also. So there are 2 orbitals, so 2 into 2, 4 electrons can be added here. So maximum, this setup can have 22 electrons. 6 plus 6 plus 6. So 12 plus 6 plus 4, 22 electrons at the max. But it is not a rule. It can be 21, 20, 19, 18, 14, does not matter.
Okay.
This is the case for the weak field ligands like I minus, Br minus, H2O, etc.
Okay.
So yeah, but whenever this the field strength of the ligand is increasing. The field strength essentially means the interaction of the ligands with the metal. Whenever that interaction is getting much more stronger, then the splitting becomes much more larger, which means that this Eg star is now becoming much more antibonding in nature. So it does not like electrons coming here, right? So so there won't be any electrons coming here. So electrons will be filling here. But still here also, it is weakly. This is also a non-bonding. No, this is also, yeah. So whenever we have more, this field strength is increasing, this gap will be increasing, and then if EG star is getting much more antibonding character, it does not like electron coming in. Still, if the T2G is non-bonding in nature, then electron can fill up here. It does not have to be like all the time. It should be filled. That kind of rule is not there. It can be 2 electrons, 4 electrons, at the max 6 electrons. So that can range up to 12 plus 6, maximum 18, but lesser than 18 is also possible, right? Yeah.
Okay.
But in this case, whenever the interaction is much stronger, now the T2G is also bonding in nature. In this case, it cannot be, in this case, definitely Eg star cannot be populated because this splitting is much, much high. And now this is the case for pi acceptor orbital. For example, carbon monoxide. The pi acceptor orbital, so the pi star orbitals of carbon monoxide is empty. Because of that, this whenever the electrons are present here, these electrons can be just, they can just give it to the pi star orbitals of carbon monoxide. And here also there is a large delta O, because of which the Eg star is highly, that is strongly antibonding in nature, and it cannot accommodate any electron. So at the max we can have 12 electron here, then 4 electron. This strongly bonded, the T2J is strongly bonded now, so it should be filled. So we will have 18 electrons. This is the 18 electron. This is the basis for 18 electron group. This happens when there is some strong interaction between the ligand and metal. This is the case for this carbon monoxide, Cn minus, PPH3, etc. In those cases, the interaction is so strong. The T2J is also strongly bonding in nature. This is a bonding molecular orbital. Eg star is a strongly anti-bonding orbital. Because of this, Eg star cannot hold any electron maximum, and this bonding orbital should be filled. That is why we have an absolute 18 electron group, 18 electrons in all these complexes. So
So, ma'am,
if
this is possible for only strong field electrons.
yes, only strong field ligands. And normally we can say that this 18 electron rule is applicable for organometallic metallic compounds. And another exception is a 16 electron rule, that is for square planar complexes. For square planar complex, this is not the splitting. This is only for octahedral. All these diagrams I have shown for octahedral complexes. So for square planar complexes, there is a different kind of splitting, and because of that, it can also accommodate 16 electrons. So there's a separate 16 electron rule for square planar complexes. For octahedral complexes, it should be 18 electron. For the strong ligands like carbon monoxide or in organometallics. Yeah, actually, I'm a bit confused in with this question. Maybe in next class I will discuss. We have some more questions, but it is already 9 o'clock. Maybe we can stop. Next class I'll discuss other questions. Or if you are okay with it, I can discuss the like these are like similar only. Maybe I can go to this Ellington diagram. Maybe explain a bit. Then maybe we can wrap up. Whatever you guys are
Ma'am,
comfortable. Yeah.
ma'am, can you please share the PDF?
Yeah. Sure. Sure. This PPT, right?
Yeah.
Actually, I have shared it with the NPTEL group, so I think they will publish it and will give the link to you guys.
Okay.
So if you guys want, I can just explain this some questions related to the L income diagram. Otherwise, we can discuss it in the next class. So whatever you guys are okay with, I am also okay with. So can you
Ma'am,
please?
I had some doubts
Yeah.
also.
Hmm. So
We
so
can
maybe
discuss later, ma'am. No
okay.
problem in
Sure,
this.
sure. So next week we can discuss. So if you have any other doubts, maybe now we can discuss. If you don't have any doubts, you can leave. It is fine. So next we will meet again next Tuesday. Same time. Yeah. If you have any doubts, yeah, you can tell. Uh,
Ma'am, there are many of them actually.
yeah.
I'll tell one of them.
Can you tell me?
Ma'am, the question is the typical electronic configuration of the transition metal center for oxidation addition. The first option is D0 and D8. Second option is D6, D8, D8 and D10, D5 and D10.
Do you have the questions? Like, can you share the screen?
I have written it in the chat box. I'll write it once again. I'll send it once again.
Yeah, sure. So if you don't have any doubts, you can leave. If you have doubts, you can stay. We'll discuss. Yeah, thank you. Thank you so much. Okay, the typical electronic configuration of a transition metal center for oxidation addition. D0 and D8, D6 and D8, D8 and D10, D5 and D10. So basically the oxidation addition is we are adding a ligand at the same time the metal is getting oxidized. So first we have to think who will get oxidized. Oxidation is basically the removal of electron, right? So
Yes.
whoever has more electrons will be oxidized. So from that, can you guess which is the more probable answer?
The C option D8 and D10 then.
Yeah, D8 and D10 can be an answer, but since D10 is fully filled, I'm not sure. It can be D6 and D8 also.
Okay.
I have to check this, but I can just give this indication. But I'm not sure if D10 will be okay for oxidation because D10 is already completely filled, and if oxidation has to
Then
happen,
I'll tell the answer also. I have
yeah.
it.
Mm-hmm.
Ma'am, the answer is D8 and D10, C option.
See. Mhm.
Ma'am, this was given on the NPTEL, the solution for
Okay.
assignment.
Mm-hmm. I will look why D6 and D8 is not preferred. Um, Next class, maybe I'll discuss.
Okay, ma'am, there are means a lot of doubts from week 1 and week 2 I had in the assignment.
Okay, so this is which assignment? Week 1 or week 2?
This one is week 1.
Week 1. Okay, so actually, the week 1, I find that the assignment questions and the class what sir has taken has no connection, right?
Okay, huh. I also felt that. It was just the basic one and this was
Mhm.
overall what we have done.
Yeah, I think these questions will come in the fourth or third week. Actually, in those weeks, I think he's discussing about the reaction mechanisms and all. I mean,
Okay.
in that classes, maybe it will be much more clear. I don't know why this year it has happened like this, but last year's assignment solutions only I have solved in this session.
Hmm.
So those questions are directly related to the week 1, whatever we solved in the first part of this session. I don't know this time what happened.
Okay. So should I ask these questions in the week 3 or today
Yeah,
only?
do you have any other questions? I can try to answer, but
One of this is number of bonds per Fe
uh,
atom in
that
Fe3.
it will come in the third week, I think, because there you'll be studying about the organometallic compounds, and there's a special formula to calculate this number of metal bonds. I think you asked me in the last class also. I
Huh.
didn't have time to discuss it this class. Maybe next class.
Okay. Then for the week 2 also I have some.
Hmm.
One of the question was the number of manganese ions in tetrahedral and octahedral sites respectively in Mn3O4 are 1 Mn2 plus and 2 Mn3 plus, 1 Mn2 plus and 2 Mn2 plus, 2 Mn3 plus and 1 Mn2 plus, 2 Mn2 plus and 1 Mn3 plus.
Yeah, this is a completely separate topic. It is called spinels. But in this spinel compounds, there will be there will be like two metals, Mn2 plus and Mn3, like metal in 2 plus state and metal in 3 plus state. So according to which metal has the highest crystal field splitting energy, it will occupy certain holes. Sometimes, like if it has a highest CFSE, it will occupy octahedral holes. Otherwise, it will be tetrahedral holes. So based on that, it can be inverse spinal or normal spinal structure. So
Okay. This one is also, I guess, week 3 because I've done today the video and there
uh,
was something related to this
So
also.
basically, you have to calculate the CFSE. If it is Mn2 plus, right? Mn2 plus means
Huh.
D5. So for
Okay.
D5 configuration, what will be the CFSE? Mn3 plus means it is D4. So for D4 configuration, what will be the CFSE? So whichever has the higher CFSE, according to that, it will be spinal or inverse spinal configuration. From that, you will have to answer. Maybe next class, if it is related to week 3, I can solve it in week 3. Otherwise, with week 4, I will solve.
Okay, ma'am. Thank you, ma'am.
Yeah. So you had another, like I think you missed one question, right? Maybe I can show that.
Yes, ma'am.
This one, right?
Oh, yes, ma'am. This one.
Okay. Just so the question is to arrange these elements in the order of the effective nuclear charge. So just by looking at it, we know that these are the second row, the second period elements, right?
Yes.
I'll just show the periodic table anyways. So this CNOFFNE, these are the second period elements. So first we'll arrange it according to the atomic number, that is CNOFNE, as I have written here, CNOFNE, right?
Yes, ma'am.
So now, if I was adding electron here, so all of these have same shell, right? Two s two p is this. Like all of them have the same shell, 2s and 2p. So if I am adding an electron, I am adding to the same orbital 2p for all these elements. But at the same time, the atomic charge is increasing. It is increasing from 6 to 10, 6, 7, 8, 9, 10. So even though the since no shells are added, like it is the same shell, the size of the atom is size of the shell is a constant, but the number of but the charge of the nucleus is increasing. Because of that, there will be much more attraction between the nucleus and the electrons in 2s and 2p. Because of this higher attraction, the atom is contracted, which means that the size is decreasing. That is why
Yes.
from carbon to neon, the size is much more decreasing from carbon to neon. So the effective nuclear charge is also what? Effective nuclear charge is the nuclear charge felt by the last electron or whatever electron that we are considered, and like which is the actual nuclear charge felt by these electrons, right? So since this nuclear charge, actual nuclear charge is also increasing, and the shell size is not increasing. Because of that, the interaction, the effective nuclear charge for this electrons are increasing, right?
Yes, ma'am.
You got it, right? Am I making it more, like, am I confusing you?
No, ma'am. It is the same as a Z star, no, that we did
Yes, yes,
earlier.
yes. So essentially, you're talking about Z star only. So Z star is also increasing in this way because the Z is increasing, but the shielding is not increasing that much because we are
Hmm.
adding into the same shell. We are not adding
Number of
any shells
electrons
here.
are increasing in the last shell.
Yes, number of electrons are increasing, but the number of shells are not increasing, which means that the shielding is not increasing that much. Whenever an electron is added, a small increase in shielding is there. But if I add if I add a separate shell, definitely that shield will be much more. Since we are adding to the same shell, the shielding is less. But if you look at the nuclear charge, it is increasing rapidly, 6, 7, 8, 9, 10. Because of that, these electrons will feel higher effective nuclear charge. So the option B is the right option.
Yes, ma'am.
Yeah,
Okay, thank you so much, ma'am.
thank you. So if you have any, do you have any other doubts?
No, ma'am, I guess they are again from the more week 4 and week 3 doubts
Yeah.
only, I guess.
Okay. So anyone else have any other doubts? Those are present. Okay. Okay. Anyways, then we'll see next week with the remaining questions and other assignment questions. We'll see next Tuesday, 7 to 9. Bye.
Bye, ma'am. Thank you.
Bye.